Welcome to Introduction to Ecology, Lesson 18. So this whole unit, we've talked a lot about species interactions, about predator-prey interactions, about competitive interactions, about mutualisms, about parasitism. The one thing we haven't talked about so much is human interactions. But we're just like any other species, and as a result, we can impact the species around us. We can impact their populations. Often we have a negative impact on the species around us. That's not universally true, but it's typical. And usually the ways we do that are either through competition for valuable resources. So we have a tendency to sort of consume resources better than other species. And that can drive the other species extinct or at least lower their populations. And the other way, of course, that we interact is through predator-prey interactions. Occasionally we're the prey, but very, very often we're the predator. And again, that tends to have a negative impact on whatever it is that we're eating. So when we think about what we do to the environment, one of the biggest things is harvesting of natural resources. And that might be things like lumber, or fisheries, or even the fur trade, where some of those early Locke-Volterra models arose from. Today, we're actually going to look at models again, but this time specifically models for harvesting. And unlike the Locke-Volterra predator-prey models that came out of the fur trade, most of the early models for harvesting actually came out of fisheries. And so they were basically built to figure out how much can I fish before I end up in trouble, before I sort of overuse my fish. So we're going to start with an equation that hopefully by now you're all very, very familiar with. We're going to start with logistic growth. But we're going to add to it. So logistic growth just describes the natural growth of a population to its carrying capacity. But if we're actually harvesting from that population, we need to add a term. We need to add a harvesting term. So there's logistic growth with harvesting. One thing you might notice is that the harvesting term is a constant. It doesn't actually depend on population size. There's no n in there. It's not like we're taking more when the fish are more plentiful and we're taking less when the fish are less plentiful. That's not what's happening. We're just taking a certain amount of fish all the time. So that's your harvesting term. And again, it's not density dependent. It doesn't depend on the amount of fish in the system. So you might think that's strange. When we did predator-prey, we had the predator taking prey proportional to the amount of prey in the system. So why do we not have that for harvesting models? I just said that people are basically other species and we basically interact in predator-prey type dynamics. Well, that's not entirely the truth, right? Because people are a little bit different, especially people in groups in things like fisheries. So if I think about a fisherman here and he might be fishing and there might be tons and tons of fish. And so he says, oh good, there's lots of fish. I think I can sell about 500 at the wharf this week. So he's going to take 500 fish. But what happens when there's a lot fewer fish in the water? Does he say, oh, well, there's fewer fish, so maybe I should take less? Nope. Typically what the fisherman says is, oh no, there's hardly any fish at all, so I'm going to have to work really hard to catch 500 fish this week to sell at the wharf. He doesn't say I'm going to catch less. He says I'm just going to have to work harder to get the amount I want. And that's pretty typical. Pretty often with humans, especially, again, humans in things like fisheries where there's large groups that work together, the effort may go up when a species is scarce, but the harvest rarely goes down until the species population is very, 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 very low, until it becomes basically impossible in the amount of hours there are in a day to catch the number of fish you want. So that's why that harvesting term does not depend on n. It does not depend on the size of the population you're harvesting. So for example, it does not depend on the fish population if you're interested in harvesting fish. So what can we do with this logistic growth plus density independent harvest model? This is our model. This is what we're going to start. This is our model for harvesting. What can we do? Well, by now you probably think, well, there's two things I can do. I might be able to find isoclines. And we tend to find isoclines when we have more than one equation because it's hard to solve much with multiple equations. Or we can actually solve for equilibrium populations. And so that's what we're going to do. We're going to solve for equilibrium populations, which is basically where the population stops growing. Basically where the rate of change of the population is zero. So again, that's very much like an isocline. The difference is with isoclines, we tend to have multiple different populations, but really we're doing the same thing. We're looking for where the rate of change of the population goes to zero, where it stops going up, it stops going down, it's at a fixed size. All right, so if I do that, all I need to do is set the equation equal to zero, because that's when the dn dt is the rate of change of the fish population size through time. And if that rate of change is zero, then the fish population is not changing through time, and that's my equilibrium. That's my definition of equilibrium. The population doesn't change when it's at equilibrium. So now that I have this equation, all I need to do is solve for n, solve for the number of fish or the number of whatever I'm harvesting, and that tells me the equilibrium population of the fish. Well, easy, maybe not, because if I actually expand out that equation, that r times n times 1 minus n over k minus h, I get a quadratic equation. So that's not terrible. It is possible to solve that. You probably did it in high school and you've probably forgotten since. To do that, we need to use that quadratic formula. And so basically, if I plug in the minus b, the a, and the c, so remember the a is the term out in front of the n squared, the b is the term out in front of the n, and the c is just the constant term without any n. If I plug those in, I end up with this equation. So that tells me the number of fish, or the number of whatever organism I'm harvesting, that I have at equilibrium. And if you remember this quadratic formula, you realize that there's two different solutions. There's a bigger solution where you use the plus sign, and there's a smaller solution where you use the not minus sign. So you might wonder, how can I have two different populations? Well, we're going to look at that. That's really the crux of these harvesting models, and this is what makes harvesting models so tricky and so dangerous when we tend to overfish them, because bad things can happen depending on these solutions. All right, so let's take a look at this just a little more briefly. If I don't have any harvesting, right, if I just get rid of my h term, I set it equal to 0, then you might think, well, then I just have logistic growth. Shouldn't this be a logistic growth equation? And in fact it is. When I don't have any harvesting, I can simplify that equation for n, and it actually equals the carrying capacity. So the population grows up to its carrying capacity, and that's the equilibrium. It stops changing. But when I do have harvesting, I have a negative term under that square root sign, and so basically I'm reducing my my population size of whatever I'm harvesting because I'm harvesting. That makes sense. I should not increase the size of the population when I'm taking stuff away. That would be very rare. When I'm taking stuff away, I'm decreasing the population size, so my equilibrium population is smaller. It might be a lot smaller if h is really big. If I'm harvesting a lot, it might only be a little smaller if h is really small and I'm not taking too much. But regardless, harvesting always reduces the equilibrium population size of the population that you're harvesting. All right, so that's how we solve for the equilibrium population size of what we're harvesting. And like I said, we have two different populations. And the easiest way to think about what that means is to look at graphs. So that's what we're going to do. I'm going to go back to that equilibrium equation that we solved. That's just the sort of setting that rate of change equal to 0. And what I'm actually going to do is I'm going to solve for harvesting on one side and then the growth rate on the other. So basically on my right-hand side, I have the population growth rate without harvest. Basically just the rate of change of the population, assuming logistic growth. Now what I can do is I can actually plot that right-hand side, which is just the rate of change of the population or the growth rate of the population, as a function of population size. If I expand it out, it's actually a quadratic. And if you remember plotting quadratics, they look like parabolas. So that's what we get. We get a parabola. And you can try plotting this out yourself. You can try different values of big N and for a fixed value of r and k, and you can sort of plot out what the curve looks like. It's always going to look like a parabola. It's always going to have that sort of up and then down. It starts low at n equals 0. It starts at 0. It goes up to some maximum point, and then it starts going down again. So what this tells us is that as a function of population size, the growth rate of the population changes. We kind of know that already. So when I have a very small population, I have a slow growth rate because there's very few individuals around to grow. And I want to make a point here. This is not the per capita growth rate. That would be dividing by n. This is the total growth rate of the population. So it includes sort of how many are in there. So when I have very, very small population sizes, overall the population is not growing fast because there's too few individuals to breed. They're not having a lot of babies because there's not a lot of things to have babies. Then as I get a bigger and bigger population size, the population grows faster because there's just more individuals breeding up until a point. And that's the maximum growth rate of the population. That's that peak in the parabola. But then as I get even bigger population sizes, what you'll notice is the parabola kind of turns over and it gets smaller and smaller and smaller again. The line goes down negative along that y-axis, and that means the population growth rate actually slows down, and in fact it crosses zero and becomes negative. What's going on there? Well, at that other end I have slow growth of the population because there's so many individuals. In other words, there's so many individuals that more can't fit. So the population can't grow any bigger. It basically stops growing because there's no resources for more to fit in there. And basically then all of my births end up balancing out the deaths and my population stops changing. We know what that is. We know when the population stops growing because it's too big, that's what we call the carrying capacity. And so on that other side where the population is really big, where the line crosses zero, where the population stops growing, that is the carrying capacity. That population size is the carrying capacity that you would reach without harvesting. Again, this is just the logistic growth equation I'm plotting because I'm only plotting that right hand. I don't have side of the equation. I don't have any harvesting in there. So I'm basically just plotting the growth rate of a logistic population model. I'm plotting the growth rate of that model as a function of population size. All right. Now here's the interesting thing about harvesting in a logistic model. So remember I said down when I have a very small population size, the population grows very slowly because there just aren't enough individuals to breed. Well, if I've got too few individuals to breed and that's why the population is growing slowly, if I remove more of those animals, I've got even fewer to breed. So what happens? The population grows even slower. So removing individuals when I'm at a very low population size actually slows population growth. And we see that because as I move down to lower population sizes, that's more to the left on the x-axis, my population growth rate decreases. I start growing slower and slower and slower. That's moving down along the y-axis. So you can see that as I remove individuals, I get a smaller and smaller population, the population growth rate gets slower and slower until it goes to zero when I have no individuals. And that makes sense. If there's no individuals, my population is not going to grow because there's absolutely no one to have a baby. What happens on the other end, though? On the other end, where I have very slow population growth rate because there's so many individuals, because they just don't fit because I'm at my carrying capacity, in that case, when I remove individuals, it actually causes the population to grow faster. Why? Well, because it frees up more space, more room for individuals to grow, to fill in, and so the population can breed faster again to fill up that space. And so you can see that on this graph, as I move to smaller population sizes when I'm at a high population size, that's as I move left along the x-axis from the high population sizes, my growth rate for the population actually increases. I go up along the y-axis. You can see that green arrow. As I move left along the x-axis, I go up along the y-axis. And that means that as my population size decreases, as I remove individuals, the population growth rate increases. And again, that's because I've freed up space, and so animals are able to breed faster to fill up that space. All right, so that's plotting the right-hand side of that equation. That's really just plotting the logistic growth rate as a function of population size. That's really all I've done. There's no harvesting in that figure at all. I really just plotted how fast a population grows at a variety of different population sizes, assuming logistic growth. So now what I'm going to do is I'm going to look at the left-hand side. The left-hand side is my harvest rate, right? That's H. That's how many I'm taking of the particular animal or plant or whatever I'm harvesting per unit time. So if I plot that, that's just a line. That's a constant, right? I might be taking 2 per unit time, or I might be taking 10 per unit time. Whatever I'm taking per unit time is just some line. It does not depend on population size. And of course, it doesn't depend on population size because as humans, we don't fish proportional to the amount of fish there. We say, I want 500 fish to sell, so I'm going to get 500 fish to sell. And so we have a flat line as a function of the fish population size. Doesn't matter whether there's 100 of them or whether there's none of them, I'm taking about 2 per day regardless, because I'm just going to fish harder on the days when there's less fish. All right, so now I've plotted the left-hand side. That was pretty easy. That was very easy to plot. Okay, and again, that's density independent. That left-hand side does not change as a function of fish population size, as a function of what I've plotted along the x-axis. because people just take out what they want regardless of how many are there. So I've got my red curve, which is logistic growth, which is the right-hand side of the equation, and I've got my blue curve, which is the harvesting rate, which is the left-hand side of the equation. And when those are equal, I'm going to satisfy that equation, right? That equation says when the harvesting rate, the blue, equals the logistic growth rate, the red, that's where I have an equilibrium population, right? And where's that going to be true? That's going to be true where the red curve and the blue curve intersect. And so you can see there are 2 points where the red curve and the blue curve intersect. Does that make sense? Yes, because where those 2 lines cross, that's the solution to the equation, and we know that that was that quadratic formula. There should be 2 answers. The low answer, where the red curve intersects the blue curve at the low population densities or low population sizes, and the high solution, the positive solution, where the red curve intersects the blue line at high population sizes. All right. For both of these, the population growth rate exactly equals the harvest rate. So I'm taking out, because of harvesting, exactly what I'm putting in because of population growth. And that's why the population doesn't change at those 2 points. That's why that's the equilibrium points. Basically, for every fish I take out, 1 fish gets born. For every fish that's born, 1 fish gets taken out. My harvest rate exactly equals my population growth rate, and so my population, the net change is 0. All right, so far so good. So we might have 2 populations. This one looks like it's at about a fish population size of 18, and this one looks like it's at about a fish population size of 68. What does this mean? Remember I said we have 2 different solutions, and this is where it gets tricky, and this is where over-harvesting can be dangerous. Let's take a look at that. Remember I said that when we're on the sort of downhill slope, when we're on the left-hand side of that mountain, when we're on the left-hand side of that parabola, we're at small population sizes. And when I remove individuals at small population sizes, that slows population growth even further, right? Because the population is breeding slowly because there's too few. When I remove more, it goes even slower because there's even less to breed. And so again, that's where we saw removing individuals, lowering the population size, causes a decrease in the population growth rate. Moving left along the x-axis causes you to move down along the y-axis. What that means is if you just slightly over-harvest from that perfectly matched point. So again, at that perfectly matched equilibrium, I'm taking out exactly what is being replaced by birth. If I just slightly over-harvest, if I take out like 1 fraction of a fish too much, that pushes me over the limit. And so then I'm taking out more than I'm putting back in, and the problem compounds, and I basically slide down to extinction. So even just a slight overharvest leads to extinction when I'm on that side of the parabola. For my solution that's on that side of the parabola. As long as I'm careful, as long as I harvest exactly a perfect match, then I'll stay at that fixed point forever. But that's not going to happen. And so instead, what happens is every so often I slightly overharvest, and then that means that I'm taking out more than I'm putting back in, so that gets me behind a little bit. And then I take out even more than I put back in because I'm further behind, and you just keep getting further behind until your fish population goes extinct. What happens on the other side? Well, remember I said on that side of the parabola, right, that's where my population growth rate slows because I have too many fish, right, or too many of whatever organism I'm harvesting. And so I'm running up against the carrying capacity. And so on that side, when I remove individuals, remember, the population growth rate actually increases. As I move left along the x-axis, as I decrease population size, I move up along the y-axis, I increase population growth rate. So that's good. And what that means is that if I over-harvest a little bit, if I sort of lower the population a little bit from that equilibrium point, the population recovers because the population starts growing faster and filling in what I've removed. And if I remove a little bit too much again, then the population just grows faster again and compensates. So basically, you want to be at that high equilibrium point because if you over-harvest, or if you sort of take a little bit more, so if you take a little bit more than what population growth rate is filling in, again, that equilibrium point is where the amount you're harvesting exactly perfectly balances the amount of population growth, the amount that the fish are being replaced because of population growth. But when I'm on that equilibrium where you want to be, if I take a little bit more than the population growth rate is replacing, it's okay because the population growth rate will speed up to fill in that gap. Don't want to be on the other side, because that's where if I take a little bit more, the population growth rate doesn't speed up to fill in the gap. In fact, it gets slower and exacerbates the problem. So you want to be at the top equilibrium, you don't want to be at the bottom equilibrium. And yet as humans, we very typically are at the bottom equilibrium or someplace else along that other sort of that left-hand side of the parabola where things are going down and it's a bad situation. Why do we end up at that bad scenario on that other side of the parabola where the population is going extinct? Or maybe it's at an equilibrium point, but just a slight overharvest, which is going to happen sometime, causes us to move down to extinction. Well, it's because we're greedy. So here's a fisherman. Here's my harvesting problem. I've drawn my logistic growth in red. I've got my blue harvest line. And the fisherman says, okay, well, maybe I'm at this equilibrium. Everything's good. I'm at the high equilibrium. If I overfish a little bit, it's okay because, as long as I go back to fishing at the right amount, the population will recover, right? But that's not what happens. The fisherman basically says, well, I'm harvesting 2.5 fish a day, maybe 2.5 fish per acre per day. But I could do better. Surely I could fish 3 fish per acre per day. And so the fisherman increases his harvest just a little bit. And so now what we find is that our equilibrium population size has decreased because the fisherman's taking out a little bit more, so the equilibrium population size decreases. But it's okay because we're still at that high equilibrium solution, right? We're still good. Everything's okay. But does the fisherman stop there? No, the fisherman says, but surely I can just harvest a little bit more. If I harvest 3 fish per acre per day, I'm not depleting my fish stock, so maybe I could just fish a little bit more and still be okay. So then the harvest rate goes up to 3.5 fish per acre per day. And what you'll notice is that we've decreased the equilibrium size of the fish population just a little bit once again, because you take out more per unit time, the equilibrium population size goes down. And the fisherman does this for a little while and he says, okay, well, the stocks seem pretty stable. So surely I could harvest a little bit more than this. Maybe I could get up to 4 fish per acre per day. So he does that, and this is where we should be yellow alert flashing. This is not looking good. Our fish population is kind of declining, our equilibrium fish population. We may not know it, but we're kind of getting close to a very scary precipice up there, that top of the parabola. But does that stop the fisherman? No. The fisherman says, okay, well, things look good at 4 fish per acre per day. Let me just try to do 4.5 fish per acre per day. And now you'll notice something looks very different. Instead of that blue line crossing the parabola at 2 different points, your 2 equilibrium solutions, your high equilibrium solution and your low equilibrium solution, all of a sudden, the blue line doesn't cross the red line at all. In fact, the blue line lies entirely above the red line. And what that means is you are harvesting more fish than the population, even at its optimal population growth rate. Even when it's at the maximum that population can grow, you're harvesting more than that maximum point. The maximum rate that population can grow is at the peak of that parabola. If your harvest line is above that, you are taking out more fish than even the best case scenario population growth rate is going to replace. So what does that mean? Well, when the curves no longer intersect, you're taking out more fish than even the best case scenario, and that means that you just can't sustain the population. The population starts dropping and dropping and dropping because you keep taking out more than is being replaced over and over and over. And so the fish population essentially is going to crash. And so it's going to start at that equilibrium it was at when you were harvesting sustainably, and it's going to drop. And so hopefully before it drops to 0, the fisherman gets smart and says, well, that was a bad idea. I see my fish population is suddenly starting to crash. It wasn't crashing when I was harvesting at 4 fish per acre per day, but now that I'm harvesting at 4.5, I see a rapid plummet in my fish population, so I better back off. And so he says, okay, I gotta fish a little bit less from now on, but that's okay. I'll just go back to harvesting at that lower level. Maybe I got scared and I'm gonna go all the way back down to the 2.5 fish per day per acre. And he says, well, that should be good. I should be okay. But what do you notice now? Well, now what you'll notice is that if that fish population dropped far enough, it's actually dropped below that equilibrium point, below that lower equilibrium point. It's in fact dropped so that now, even harvesting at 2.5 fish per acre per day, you are harvesting at a higher rate than what the fish population can sustain. So if that fish population is at about 10 to 15, then it's replacing about 1.9 fish per acre per day, right? Because that's where that black dot is on the y-axis. It's replacing about 1.9 fish per acre per day. So if you're harvesting at 2.5, you're still taking out more than the fish population is recovering. And the reason is you're taking out more than the fish population is recovering because that fish population is so small, it's just not breeding fast. There's nobody to have babies. And so you're not breeding at the same rate you used to be when the fish population was high. So again, your population growth rate, that red curve, lies below the harvest rate, the blue curve, at that particular fish population size that you've got to, right? So again, we're at somewhere between 10 and 15 fish in that population. And you'll see that at that particular point on the x-axis, if I drop to that black dot, I am hitting that red curve first. That means my population growth rate is lower than my harvest rate. And so it's too late. You can't go back to where you used to be and be okay because the population is already on its way to extinction. We've crossed the turning point. And so the fisherman says, wait, what? I have to fish less than I was able to fish before? In fact, quite a bit less than I was able to fish before? Why is that? I mean, I was able to fish 2.5 fish per day per acre and I was okay. In fact, I could get all the way up to 4 fish per acre per day and I was still okay. And the reason he's not okay is because he's caused those fish stocks to decrease to such a small size that the population just isn't replacing itself at any rate relative to what you want to fish out. All right. So basically, to get this population to grow, this fisherman has to harvest at a level lower than the population growth rate of the fish. So if I take a look at the population growth rate of the fish, that's the red line. I have to harvest at some rate lower than that. Because again, if I'm harvesting less than the fish population is replacing by natural birth, then it's okay. I'm going to get more births, take it a little bit less, more births, take it a little bit, and my population's going to climb. So what that means is my harvest there has to be somewhere quite a bit below 2. It has to be about 1 fish per acre per day in order to allow the stocks to recover. And as long as I harvest below, at some level below where I'm at on that red curve, then the fish population will grow. But of course, the fisherman says, that's hardly any fish at all. I mean, at the best of times, I was harvesting at almost 4 fish per acre per day, and things were okay. Now I have to drop all the way to 1 fish per acre per day? You're telling me I have to do that? That's going to take a massive economic hit. And so, if all fishermen were smart in the first place, they'd say, well, I shouldn't have done that. So next time I'm in this situation, let me be a little more careful about how much I fish. What is the most I can take out and not end up causing the fish population to crash? So what's that maximum harvest I could have taken out and still been okay? Well, it turns out that maximum harvest that won't deplete the stocks is the amount of harvesting you can do where your blue harvest line exactly touches the maximum point on that parabola at a single point. So if I draw that right there, you see that blue harvest line where it touches that parabola at one point, where it touches the parabola at the maximum point, that is the maximum harvest. Because that's as fast as the fish population will grow. So if I harvest to keep the fish population size at exactly that value, where it's basically reproducing as fast as it possibly can, then that's the maximum harvest I can possibly get out of that system. So we call that harvest level, the amount you can maximally take out, the maximum sustainable yield, the MSY. So that's basically the value along the y-axis where you can draw your harvest line to exactly touch the parabola at one point. So again, that's the maximum sustainable yield. That's the largest harvest rate that can be sustained without reducing the stocks. And it's basically the maximum growth rate of your population. It's the sort of growth rate of the population at the peak growth rate. So in this particular case, my maximum sustainable yield looks like it's about 4.1 fish per acre per day. And if I harvest at exactly that level, then I will have some sort of intermediate population size that I can sustain forever and ever and ever. And so again, this is associated with the minimum population size that I can possibly push the stock to without causing this fatal crash in the fish population. So if I push the fish stock any smaller to any smaller population size, then a crash is imminent. And so in this particular scenario, for example, it looks like that at my maximum sustainable yield, I can get 40 fish per acre. And so the minimum population size that I can push this population to is 40 fish per acre. And if I push it any lower than that, the population gets into this feedback where it just crashes and exacerbates your fishing problem. All right, so there's my maximum sustainable yield. Any harvest level that is above that, you're over harvesting. Any harvest level below that, you're actually under harvesting. You could harvest a little bit more and still be okay. So you're not harvesting as fast as you could under ideal conditions. In reality though, although we might try to do this, it's dangerous to harvest at the MSY. And it's dangerous because harvesting is not an exact science. In fact, you don't really know how many fish you're going to get from one day to the next. And you don't really know what other factors are affecting that fish population size. So if you're harvesting at exactly the maximum sustainable yield, and any tiny little thing, any small perturbation, like a storm that kills one fish, or some other guy that's fishing a little bit more next to you, anything, just the tiniest loss of one individual fish pushes you below the population size that can recover, and basically you get into this feedback cycle where all of a sudden you're slightly below your harvest rate, and then you're more below your harvest rate, and more below your harvest rate, and you drop until the population goes extinct. So harvesting at exactly the MSY is dangerous because you just don't know when some random thing like a lightning strike is going to push you slightly below it. So ideally you would harvest just above the MSY, above enough that you're safe from any random fluctuations, random environmental events that might push you below, but you're getting the most you can out of that system. So give an example from my home country. In the early 90s, Canadian cod populations plummeted, and this was a result of overfishing. It's not clear they were even aiming for the maximum sustainable yield. They were just aiming for a lot of fish. And so the government basically stepped in and said, hey, we cannot harvest cod like this. We're going to drive cod extinct. And so they actually they provided financial support to fishermen so that fishermen could still survive. They provided retraining programs so that rather than being fishermen could trade and do other things. But you see that massive plummet in the 1990s of the cod stocks. And in a very recent, about a year ago, article, the Canadian News reported that actually the cod was rebounding. So this is actually interesting to me because I went to college out in the east coast of Canada. And so a lot of the people on the East Coast were cod fishermen, or at least their parents were cod fishermen. And so a lot of them experienced this sort of crash in their parents' industry. And just now, I went to college a long time ago, just now we're starting to see those cod populations rebounding. We're starting to see the cod fishery recover in the East Coast of Canada. But again, it's still low even 20 years later, but it is at least recovering. All right, so that's harvesting problems. They're good for fisheries, for forestry, for really anything that humans like to harvest from the natural world. So now we're going to move on to a somewhat different topic. We're going to talk about disease dynamics. And since it's Halloween, or for those of you watching this at another point, it was Halloween, we're actually going to talk about vampires. So let's start with some town folk. There we go, and we're going to call them H. These are our town folk. And if we have a vampire arrive in town, that vampire is going to start attacking town folk. So here's my vampire, we'll give him the symbol V. Now the interesting thing about vampires is that they get really excited about sucking blood, and when they do that, they actually turn the person they suck the blood from into a vampire. So this is basically the way that vampirism spreads. And then these two vampires then sort of seek out new victims, and they bite them and they turn them into vampires, and they seek out even more victims and they bite them and turn them into vampires until the whole town is basically a pile of vampires. So we want to describe this with a model, with a mathematical model. And the simplest way that we can describe this is to say, well, I'm going to look at how the number of townfolk change through time. And typically they're just disappearing. They disappear by running into vampires. And then I'm going to look at how the number of vampires changes through time. And they basically appear because the vampires, by biting the townfolk, create more vampires. They turn the townfolk into vampires. So that first equation describes the loss of humans, the loss of the townfolk. And basically it says that townfolk are being lost at a rate proportional to sort of how fast vampires run into and hit them. So the more vampires I have running around, the faster I lose humans. And the more humans running around, the faster I lose humans because there's just more humans to run into. The other equation describes the gain of vampires. And again, for every human I lose, I gain a vampire. So it's not surprising that the first equation matches the second equation except for the sign. I lose 1 human, I gain 1 vampire. I lose 10 humans, I gain 10 vampires. And again, this is a mass action just like we saw for Locke-Volterra predator-prey. The assumption is that if I double the number of vampires, I double the rate at which humans get converted into vampires. If I double the number of humans, I double the rate at which humans get converted into vampires. That's the assumption of mass action. That's the assumption of multiplying the number of townfolk H by the number of vampires V to get the rate of change of townfolk and vampires. All right. So here's my townfolk again. I'm going to add another complication to this model to make it sort of match more standard disease models. I'm going to say that I have a vampire hunter. And this vampire hunter can actually seal vampires into coffins. And that basically removes vampires from the system. They got a certain amount of time they can hang out in the system before they get found by this vampire hunter, who is A, protected from being a vampire himself, and B, just goes around killing vampires. All right, so here I have my vampire come in. He sees some townfolk, he gets really excited. He wants to suck their blood, and there he goes, sucking the blood. Turns that guy into a vampire. Off we go. We bite some more townfolk, turn them into vampires, but then all of a sudden the vampire hunter starts doing his job, and he basically seals these vampires into coffins. All right, but he doesn't get them all, so they continue to move through the population and spread vampirism. So again, I have the same equations I had before. I have the rate of change of humans, and we're losing humans every time they get turned into vampires by running into vampires. Then I have the rate of change of vampires, but now I've got to think about an additional term. So I have a gain of vampires by vampires biting humans and turning them into vampires, but now I also have a loss of vampires. And that loss of vampires is because I have the vampire hunter sealing them up in coffins. So that's my loss term. It's negative. I am losing vampires at a particular rate because they're now being sealed into coffins by the vampire hunter. Now, when they seal into coffins, that means they turn into coffins. And so I can write a third equation where I think about the number of coffins, or the rate of change of coffins in the system. And basically for every vampire I lose, because the vampire hunter finds them, I gain a coffin. So it's not surprising again that the negative term in the second equation, that minus alpha v, which is my rate of loss of vampires, is exactly the same as that positive term in the coffin equation, the rate of gain of coffins. So there's my coffins. All right. Now, what I want you to notice is that it doesn't really matter whether I'm a townfolk or a vampire or a coffin. I sort of have a one-to-one substitution there. So for every townfolk, I'm going to end up with either a vampire or a coffin or a townfolk left over, right? And what that means is that the sum total of the number of humans, vampires, and coffins remains constant. So if I go back to my townfolk, I have 1, 2, 3, 4, 5, 6 townfolk, not counting the vampire hunter. If I turn some into vampires and coffins, I still have 1, 2, 3, 4, 5, 6. Although now I have 1 townfolk, 2 coffins, and 3 vampires. But the total is still 6. And sorry, I didn't count that vampire out on the outskirts in any of my counts. All right, so because the sum total number of humans and vampires and coffins remains the same, I can write the total number of anything in the system, coffins, vampires, or humans, as the sum of the 3. And because of that, if I know the number of humans and I know the number of vampires, I can automatically figure out the number of coffins. It's constant. And so I don't need to keep track of that third equation. I can just figure it out by adding up the other two and figuring out what's left over must have been turned into a coffin. All right, so there's my equations. And what I can do is I can actually represent this system as a flowchart. So in this particular example, I can go from a human to a vampire by being bit by a vampire. And that happens with a rate constant beta. Beta is the rate constant at which vampires find humans. The next progression, I can go from a vampire to a coffin. I can't go from a vampire back to a human. That's not happening, right? There's no way for that to happen. But I can go from a vampire to a coffin. So my next arrow takes me from vampire to coffin at a rate alpha. So that's the rate at which the vampire hunter finds vampires and turns them into coffins, seals them into coffins. And again, I can't go back from a coffin to a vampire or a coffin to human. There's no way for that to happen in this system. So there's my flow chart. And those three different boxes, the humans, the vampire box, and the coffin box, we call those compartments. And so this is basically what we term a compartmental model. We have these three different compartments, humans, vampires, and coffins, and we have flow between them. In this case, the flow is only in one direction, from humans to vampires and from vampires to coffins, and those flows happen at particular rates, described by the rate constants beta and the rate constants alpha. All right, so in this system, there's really two possible outcomes. First, the vampire population may initially rise and then decrease again as everybody gets turned into coffins. And when that happens, the human population rapidly crashes. Another population is that the vampire population may just decrease right from the start. It may never really get a chance to take off, right? The vampire just doesn't, the first vampire into that system just can't find enough humans to spread the disease and get it going. So, in the first case, where the vampire population takes off and basically, blows up and then eventually burns out, we say that the vampire-free equilibrium is unstable, right? It's unstable. If I add just a few vampires to the system, the whole system ends up turning into vampires, and then eventually the whole system, or almost the whole system, ends up turning into coffins. That's the vampire-free equilibrium is unstable. You can't remain at the vampire-free equilibrium indefinitely. In the other case, where the vampire population just can't take off, it never gets going enough to take off, we say that the vampire-free equilibrium is stable. So it's stable to have no vampires in that system. Even if you add a few vampires into the system, they don't take off, you just return back to the vampire-free state. And so in that second case, many humans remain. So take a look at those two graphs, the blacks are the humans. In the first case, where the vampire-free equilibrium is unstable, the human population crashes and doesn't recover. In the second case, I lose a few humans as the vampire sort of bite one or two that they can find, but ultimately the vampires go extinct and the human population remains pretty high. All right, so what determines whether vampires can take over a system or not? What determines whether I end up in that first case where I have nothing but coffins, or in that second case where I have nothing but, or where I mostly have humans? Well, if I look at my equations, this is my vampire population equation. And it says that, my rate of change of my number of vampires is the number of new vampires I'm making because vampires are biting humans, and the number of vampires I'm losing because the vampire hunter is finding them and sealing them into coffins. So in order for vampires to be able to take off, in order for vampires to start spreading through a population, then the rate of change of vampires has to be positive. I have to have an increasing number of vampires when I start from very few vampires. So if I start from like one vampire who arrives into the system, then my rate of change of vampires has to be positive. If it's negative, that vampire just can't spread enough. And so what that means is I can take that equation, I can take that right-hand side. Usually we're used to making these differential equations equal 0. In this case, we just say it has to be bigger than 0. It has to be positive. The rate of change of vampires has to be positive for that vampire population to grow. If it's not positive, the vampire population is crashing, it's decreasing. But it has to be positive at a very special point. It has to be positive at when the vampire population is very, very, very small, or basically 0. And that's because we want that vampire population to take off when I basically don't have any vampires in the system. That's what allows it to grow up to a certain size and then crash. So in that case, I'm looking at the initial human population at time 0, at the time when I introduce just one single vampire. And I'm looking at the vampire population at time 0, when I introduce just one single vampire. And so as long as that's positive, when I start with very, very few vampires in the system and mostly entirely a whole town of humans, if that's positive, then that vampire population can grow and we have the disease-free equilibrium being unstable. So if I rearrange that equation, I basically just solved for it. I've just solved for, I basically just rearranged it. I get beta times the number of humans in that initial state, when I have basically no vampires, divided by alpha. So alpha is the rate at which I'm losing vampires because they're being turned into coffins, right? So if I have low rates of vampire hunting, that tends to make this criteria for the vampire population being able to take off more likely to be positive, right? That makes sense. If I'm not catching the vampires quickly, then it's easier for them to sort of get vampirism spreading. We also have to have high rates of vampire attack, very thirsty vampires. So that means if my vampires are really fast at finding new humans to bite, again, they're more likely to get vampirism spreading through the population because they're just finding people faster, and so they're able to catch a pile of people before they get stuck in a coffin. So basically it's that balance between how fast can they get the next person before they get caught themselves. And so as long as they're getting more people, getting a decent number of people infected or a decent number of people turned into vampires before they get caught themselves, then the disease or the vampirism can spread. However, if they're not catching many people, if they're not biting a lot of people before they get caught themselves, then they aren't able to spread vampirism, and vampirism can't take off. The vampire free equilibrium is stable. The system tends to recover to a vampire free state. All right. So that criteria, that beta H naught over alpha, we call that R naught. That is the basic reproduction number. So here's your basic reproduction number. R naught is basically you can interpret R naught as the number of new vampires that each existing vampire generates when the density of vampires in coffins is very low, when you mostly have just humans. So if I introduce one new vampire into a huge population of nothing but humans, then R naught is the number of new vampires that single introduced vampire can make before it gets caught. So different disease models will give you different expressions for R naught. They're not always as simple as this particular expression. However, it's always true that when R naught is less than 1, the disease cannot spread. So in other words, in that case, the disease-free equilibrium is stable. The disease or the vampirism does not take off. However, when R naught is greater than 1, vampirism or disease can spread. In other words, the disease-free or vampire-free equilibrium is unstable. You end up moving away from that disease-free or equilibrium-free equilibrium. All right. Ultimately, again, this comes down to the fact that if every existing vampire makes more than one new vampire before it gets caught, before it gets locked into a coffin, then the disease can spread, or the vampirism can spread. So say I start with this vampire, he catches 2 townsfolk before he gets turned into a coffin, and each of those catch 2 before they get turned into a coffin, and each of those catch 2 before they turn into a coffin. You'll see that, we are basically spreading disease. And in that case, vampirism spreads through the population until you have almost no townfolks left. However, if every existing vampire makes less than 1 new vampire before it gets caught, here I've got 2 vampires, and maybe between the 2 of them, they can only manage to turn 1 townfolk into a vampire. They're not replacing themselves, basically. I had 2 vampires, and now I've got 1. Maybe that 1 vampire does succeed in biting 1, but then maybe she kind of fails, and now we've got some coffins, and the vampires have died out. So in this case, vampirism cannot spread through the population because each individual vampire made less than 1 new vampire before it was locked into a coffin. So, again, when we're talking about R naught, when we're talking about the stability of the vampire-free or disease-free equilibrium, we're thinking about whether the vampire can make more than 1 or less than 1 new vampire when it comes into a completely sort of untouched town population, right? When it comes into a town that's entirely humans with no vampires and no coffins, can it succeed in propagating itself? Can that vampire succeed in getting at least 1 new vampire made in that population? Eventually, even if the disease-free equilibrium was unstable, even if you get a lot of vampires, made, eventually vampirism dies out because eventually the entire town ends up turning into vampires and then turning into coffins, and I've got nothing but coffins. So when I do that, I have no vampires left, but I also don't have any humans either, or very many humans. There will always be a few humans who escape. And that's because once you get very, very few humans, once I have 1 human left in that population, it takes a lot longer to find them. And so the vampires wander around and they just can't find that last human before they get turned into a coffin. And so typically in these models, you will have a few humans left over, just one or two at the end, even once the vampirism or the disease has burned out, even once the entire population has been turned into coffins. So again, it takes too long to find that remaining human, and so the vampires get, because the humans are just so scarce and so rare, so the vampires get caught before they can create more vampires, and the outbreak eventually comes to an end. All right, so I know it's Halloween, we talked about vampires. Vampires aren't real, so why do we talk about them? Well, the model we just studied is known as the Kermack-McKendrick model, and it was actually developed to study disease outbreaks and epidemics. So when we talked about humans today, those are actually susceptibles. Those are people who have never had a disease before. When we talk about vampires, those are actually infecteds, people who have a disease, currently have a disease. Maybe it's tuberculosis, maybe it's HIV, they have a disease, and so they're called infecteds. And then what we called coffins are actually our recovered individuals. Those are people who have gotten better. They're immune, so they cannot be turned back into vampires, but they're also not going to turn into susceptible humans because they have an immune system response and they're protected. So this is also known as an SIR model, S for susceptible, I for infected, and R for recovered or removed. And it's a very, very common way of modeling disease dynamics, how a disease spreads through a population. So we looked at how vampirism spreads through a population, but it's really the same model for how any kind of disease, it's the baseline, simplest model for how any disease spreads through a population. All right, so on that note, I'd like to say happy Halloween. I hope you enjoyed our vampire study. And just a warning note that the next lecture, lecture 19, will not be filmed. We are just going to work on problems in class. So we're going to work on competition problems, we're going to work on harvesting problems, and we're going to work on epidemiology or SIR model problems in class. So do not expect it to be filmed. It will not be up online. If you have any questions, shoot me an email. Otherwise, have a wonderful Halloween.